All right, continuing on with chapter 4. This is going to be a quick test, but I just want to give you a sort of a quick primer on this. We're going to get into this more in a bit, but here I have a block that's supported by 2 ropes, and I want to know what is the tension in this rope right here. What I want to do is set up a method that we'll follow, and we've sort of been using this with some of the Newton's laws problems, but this method is, first I want to draw my vectors, or draw the forces in particular. So you need to know what all the forces are. Second, I'm going to draw a vector diagram. Third, I will resolve my vectors into x and y axes. Resolve my vectors into x and y components, rather. And then fourth, apply Newton's second law. So F equals ma. I'm going to get you up to where you can find the answer for this, but then I'm going to leave it. So here I have 3 forces acting on this block. So I'm going to take step 1, identify the forces and label them. So I have a force there. I'll call this Ft. And I have a force here. I'll call this Ft. Actually, I'm going to differentiate between these. I'll call them FTL and FTR for force tension on the left and force tension on the right. Though, as we'll see, they're going to be equal. And then I also have the weight of the object, which is Fw. All right, now I want to draw a vector diagram. This is where I'm going to identify a coordinate system. My coordinate system will be pretty simple. That'll be my x. That'll be my y. So I have my x and y axes. I have FTR, FTL, and then I have FW. Right. I also want to identify what is this angle. Well, I know that this angle is 50 degrees, so if that angle is 50 degrees, this angle also has to be 50 degrees. So I'm going to label that 50 and 50 on both of those. Then I'm going to resolve my forces into their x and y components. By the way, this first step and this second step might be combined. Once you have more practice, you might just be able to combine those steps where you draw your vector diagram on the actual figure labeling all the forces. Okay, so now I'm going to resolve my vectors into their x and y components. I will have FTR. That's going to be the x component, so it's cosine of 50. This will be FTL sine of 50. Excuse me, cosine of 50. And then over here, I'm going to have 2 vectors. Both of them are going to be FTR sine of 50. That's the y component of the right one. And then FTL cosine of 50. And then I also have the weight, which I'm going to go and label as m times g. That's 23 kilograms times 9.8. Now, from Newton's second law, that's the third step. Now in the fourth step, I say that the sum of the forces equals ma. In particular, I say the sum of the forces in the x direction equals max, and the sum of the forces in the y direction equals may. Okay. So in both of these cases, the acceleration equals 0. The object is not accelerating either in the x direction or the y direction. So both of these are going to equal 0. The sum of the forces in the x direction equals ma equals 0, and the sum of the forces in the y direction equals 0. So over here in the x, which I don't really need to do, but I'm going to do just to illustrate something, I can show that FTR cosine of 50 minus FTL cosine of 50 equals 0. So I can show then that FTR equals FTL. Because if I bring the FTL over to the right side, divide both sides by cosine 50, that cosine term goes away. Let me also note here that I did the vector sum here. So FTR is positive, and FTL, which is in the negative x direction, I list as negative. All right, so that's the you should sort of know that intuitively, that you have these two ropes at the same angle. They're going to have the same tension. The weight of the block is evenly distributed, but we show it there. And then in order to solve for Ft, I can ask myself, what about the forces in the y direction, and apply Newton's second law in the y direction. I'll leave that for you to do. I'll address that in the quick test solution. Now, when I'm looking at the units of force, the SI unit of force is the Newton. When I abbreviate units that are based on people's names, as this one is, Isaac Newton, it's abbreviated with a capital letter. In the United States, of course, the unit for force is the pound, which for reasons unknown to me is abbreviated LB, or sometimes you see it as a number symbol as the unit for the pound. People weigh about 700 newtons. A small apple is about 1 newton. In fact, a pound, or excuse me, 1 newton is approximately equal to 1/4 of a pound. So I always like to say that, like, for example, at McDonald's, you have this 1/4 pounder with cheese, you know, that hamburger that you can purchase at McDonald's, that it's actually a newton in weight. So you could call it a 1/4 pounder, or you could call it a Newton burger. I think that would be kind of cool to go there and ask for a Newton burger and see what they ask. So 1 newton is about a 1/4 pound. We're going to be using basic SI units for these units. So when we build the Newton is actually comprised of a number of different SI units. Remember, we had those basic SI units for length, mass, and time. So here I have the equation for force from Newton's second law. Mass is in kilograms, and acceleration is in meters per second squared. So these are the basic SI units for the Newton. It'll be useful for us to know these, especially if you follow dimensional analysis in order to check your answer. To be able to follow through those units is useful. And sometimes I'll just ask you explicitly on quizzes or exams or whatever, what are the basic SI units for this? So this is really the first time that we've encountered a unit that is a new unit, the Newton, that we express as separate, but is actually built upon the basic SI units of length, mass, and time. So you need to know what that is. And it's pretty easy. If you know the formula, the equation, to give you that unit, then you just plug in the basic SI units. Let's see, in the United States, the British unit for mass, the United States uses the British system. The British unit for mass is not the pound, but it's the slug. You don't really need to know that, but I think it's kind of interesting. Because, you know, when we buy stuff in the grocery store, it's based on weight. But really the appropriate way to do that should be to base it on mass instead of weight. But, you know, who wants 5 slugs of sugar? Yeah, so there's some quick tests. Those will come up later. All right, let's look at Newton's universal law of gravitation. Actually, let's go back here. I have a video I'd like for you to watch that's based on the difference between mass and weight. And so you can watch that video. I'll have a link right here for you to watch. I think that's a good place to stop. I'll pick back up with this in a few minutes.